Hey all, welcome to another session with me, Varun at OdinSchool. And in this session, we would be looking at what is SVM. As we all know, we would be going a bit deep than just discussing about SVM at a subsurface level. And this is a part of the advanced machine learning course with Python. So now going forward, for all those of you who are here for the first time, machine learning, as we all know it, is a very important part of artificial intelligence, correct? And artificial intelligence also co-hosts deep learning and machine learning and also some other technologies. Uh, one of them could be IoT, that is Internet of Things, right? So here we would be focusing on machine learning, and we all know machine learning is the hot cake of 20th century, and there are a lot of jobs in and around this module. And to give you an introduction about Odin School, guys, we at Odin School, we are a technology upskilling platform and we would help you continuously acquire new skills. Thereby, you could stay skilled and stay ahead. And my name is Varun. I come with an experience of 7 years wherein I've been working as a developer and a trainer. And over these years, I've been able to gain knowledge on HTML, CSS3, JavaScript, R, Python, and also technologies like mobile application development, SAP, machine learning, etc. All credits to the different organizations that I've been associated with. So now going forward, the agenda of this session would be to talk about non-linear SVM and also some other kernel methods that are associated with regards to SVM. Now, when we talk about an SVM or what is SVM, like if someone asks you the definition of what an SVM is, we all know that SVM is one of the best variants of classifier, and not just a classifier, it can also work very gracefully on a regressor too, or as a regressor too, right? So when we talk about SVM, there are a lot of different methods, or there are a lot of methods. Just to name a few, we know that the first one is polynomial. We have sigmoid. Sigmoid is a very famous one. It's very frequently used. And then we have linear, right, guys? We have RBF. I mean, these are just a few of the kernel functions that I'm able to remember. But even before this comes a very important question, that is, what is a kernel? Guys, kernel is nothing but a set of a code, okay, or probably it's a code with a predefined formula, right? Here, let us just go and understand about it. So these are set of different types of algorithms that are being used for pattern analysis. All right, and they are used to solve non-linear problems with the help of a linear classifier. Now, is this something very similar to logistic regression? Because even in logistic regression, we can solve uh, problems which are linear in nature using a linear classifier. But here, the advantage or probably the benefit, or how this is one step above, is here we could solve non-linear problems as well. So with regards to this, we have different types of kernels that come into picture. Okay, now you could introduce a kernel function for a sequence data or a graph or probably a vector or any kind. Okay, and the most type, or the most famous type of kernel that is very frequently used is RBF. Now why RBF is very famous? RBF. Now why is this kernel very famous? It's because it has a localized and a finite response along x-axis. Guys, this might be a very very important interview question as well. You might want to make a note of it. Now the kernel functions which we use, they return the inner product between 2 points in a suitable feature space, right? So this is the first part. Now there are also some rules that we would have to follow when you are working on kernel. I mean, that rule is from moreover from a mathematics perspective, Okay, so yeah, now as we know, these kernels which we're talking about, they are employed or they're used in SVM either for a classification or for a regression as well, or for a regression problem as well. And the SVM uses what is called as a kernel trick, wherein the data is transformed and an optimal boundary is tried to find out between the possible outputs, or for the best possible output is also what you can say, right? And there are a lot of real time use cases of SVM, or probably of kernels, using kernels as well. I mean, not to forget that. So now, going forward, this is what a kernel basically does. So here, as you can see, let me just come up with this. So yeah, this is a 2D image while this is a 3D image. Now, basically, if you can, you probably try to visualize this, this is the same data which is here, but this is probably a top view and this is a side view. Imagine you are on a flight and trying to take a look at the mountain. So this is the top part of the mountain and this is the bottom part. While now imagine you are standing around 10 kilometers, or probably 5 kilo, or probably 5 kilometers away from the mountain, then you would be able to cross sectionally divide the mountain, right? And that is exactly what is happening here. So whenever we use a kernel method generally transforms, or it upgrades the dimensionality. Now, what happens when you kind of upgrade the dimensionality is, you would see that your image, or that your data points, can be easily separated now, right? So that is how, or and that is where we could use kernel method for. Right, guys. So I hope this is understood. And if you have any queries, please feel free to revert to us on any of the mailbox, or probably the comment section below. And me or my team, we would get back to you at the earliest. Now, here, when you notice that we are using an SVM, SVM uses different real-time applications. Like, it can be used very widely in face detection. All right, because here we would be able to create a boundary around the face, right? So we use the concept of a boundary. Then this can be used also for image classification, or probably in something like protein synthesis, right? Now, how would we apply this in protein synthesis? Here you have something called as protein remote hematology, or I'm not sure if it's hematology or homology. This is something to do with medicine. So we have something called as PRH detection. That is where SVM is used. It is also very widely used in handwriting applications. All right, and another is generalized predictive control. Right, so we can use SVM based GPC to control the dynamics. All right, guys. So this is basically a dynamic controller. So these are some real-time case studies that we have associated with this module, or with this kernel, or with this algorithm, that is SVM. Right, guys? I mean, we can also go deep into and understand how are each of these classified. Okay, but then it is not required right now. Here, even, let us just consider a small example. Let us talk about PRH. When we talk about PRH, you would notice that how the protein sequences are basically modeled, and after they are modeled, they are separated, and then in the process of separation, the kernel function is used. Then you have handwriting recognition. In handwriting, you have different types of entries for validating signatures, or document prints, or etc. right guys? And here also when we talk about GPC, this is for stabilization. Okay, this is for local stabilization of the target. Cool. So these are the two areas, or these are the two places, or these are the two fields wherein we use this one and this one, wherein we use SVM at a very high level, right, guys? So these are some practical use cases of SVM. Now going forward, what are the different types of kernel functions that we use? So here I've just mentioned a few. Let us just discuss a few of them. Uh, right, so this is the one. Kernel function is to take data as input and transform it into the required form. So that's what we were talking. Now 2D to 3D or lower to higher dimension is one of them. Right guys, there are also other ways to transform and other methods which do the same thing. Now every SVM algorithm uses different type of kernel function, and these functions can be of different types like linear, non-linear, polynomial, radial. This is what we were talking about, and they are also known as RBF and sigmoid. So radial basis function is RBF, and then we have sigmoid, and as we all know RBF is one of the most used variant. Then present kernel function for sequence, data, graphs, text, images as well as vectors, and RBF is frequently used kernel because it has restricted and infinite response along the entire x-axis, and this is also something that we discussed just a while back. So here is another visual example or visual representation of how different modules or probably how different kernels react. So the first case is something that we have seen. We've already covered what is a linear regression or probably what is a linear variant of classification, either which ways. Right guys, this is a linear classification. And what is the difference between regression and classification? In regression, if in this case like here in regression we would be able to find out the relationship between x and y, right guys? But when we talk about classification, there is no relationship that is, we're not running behind finding out a relationship. We are more concerned about separating them, or coming up with the best possible distinction between them. Right guys, now this is what we mean by linear. Then in the next or the second that we have is polynomial. Now here in polynomial we are able to notice how there is a curve that has come up. This is third level or third polynomial wherein you see you have 1 and 2. Then we have radial basis. Now radial basis is round. So here we have clusters. So this is one cluster and this is another cluster. So I think radial, that word speaks a lot. And finally, we have one which is sigmoid variant of SVM classification. And guys, in sigmoid, unlike all these variants, we would not be having only one hyperplane, but here we would be using two hyperplanes, and each hyperplane would create one individual border. Right, guys? So these are the different types of SVM or different types of kernels in SVM that we use on a real-time footnote. Well, this is the formula of a couple of them, just to understand a few. The first one is polynomial kernel, and polynomial is very famously used in image processing. The second one that you can see here is Gaussian kernel. Gaussian kernel is used when there is no prior knowledge about the data. So here every time your data is learning at new. While in polynomial, it can be used for image processing, or it can also be used for other classification methods as well, like handwriting, image processing, or handwriting identification. Right. So these are the two broad areas where we could use polynomial kernel, just to set an example. Now, let me take you through to the code. Right, so as you can see, this is an SVM variant, and here what is it that we are doing? I'm importing a couple of libraries as known to all of us, that is NumPy, Matplotlib, and Pandas, and then I'm importing my data set as well in the second payload, and in my data set, the data which we are using here is social network ads. Right, guys, after which in my second step I would be now using a linear variant, right guys, and after I use my linear variant, but then even prior to that I'm using my model selection, coming up with my test train split, wherein I would be dividing my test and train into 25 and 75 respectively. After which I am considering my x and y also to be a part of the train test split, and then I'm giving a random state of 0. Random state basically ensures that whenever you are coming up with whenever whenever there is a new variant of classification, or whenever you have an answer, or whenever you have an output, your answer always remains the same. If you probably try to change the random state, you would be noticing that your answer would also be varying each and every time based on the random state number that you provide, right? And then the next one is feature scaling, or in the next step I would be working on feature scaling, and here I'm using my standard scalar. And guys, I hope you all know what feature scaling is used for, or where and when we use this, because this is something that we have already covered in our previous classes, right? So in my feature scaling, I'm pushing this into a variable which is sc, and then I'm training my model, and then I'm using fit transform, passing my x train into it. The same is the step that I'm doing for test as well. And I hope we all know that feature scaling is used to normalize the data. Let me just write things down for all those of you who are here for the first time. Right. It normalizes the data. It is also called as data normalization, guys. Please remember this. And it is a pre-processing step. We all have already seen this video on pre-processing. Okay, now if we don't use this, then what would happen? I mean, let us assume that I am not performing feature scaling. Now, in this case, you would be seeing values which are very higher, or probably even low values would be seen very high, and we don't want that, right, guys? So here I am performing my feature scaling. I'm doing fit transform on my x train, and I'm using transform on my x test as known. Then in the next step here, we are using an SVC wherein the kernel is linear. Please note the kernel is linear here, and we are again considering the random state of 0 and fitting this to the train model now. Okay. Now going to the next step here, we are using a confusion matrix, and we know that 66 plus 24 divided by whatever is the total would give us the value. So what is 66 and 24? it is 90, and this 8 plus 1, 8 plus 2, which is 10. So 10 and 90. So now we see that we have an accuracy of 90%, or you could also say that we have 10 incorrect predictions, which means that this is a beautiful qualifier and also a beautiful classifier, to be very honest. And then let us also just go ahead and take a bit of a sneak peek into how the image looks. Now this is a linear set. Guys, please make a note very carefully that when we use this, you have only one line. This is a linear line, right guys? But what would it be like when we move on to SVM? Like how would RBF or probably Gaussian, how would they react? Now this is something that we would have to find out, or we would have to know in the video as we keep going forward. Right, so here I have another code. I was just testing this. Let me just remove all this. Alright, so as you're able to see guys, the same set of three libraries once again, which is NumPy, Matplotlib and Pandas. In the second step, we are reading the social networking ads, CSV, and after that, I am using my X and Y, which would define my independent and dependent variables. So within my X, I have 2 comma 3, and within my Y, I have 4th. Right? Let us now execute the first 3 steps. Done that. Execute the data set in the second 3. Alright, so here I have my data frame. There's 5 columns in total. 1, 2, 3, 4. Okay, alright. 1, 2, 3, 4, 5. So these are the 5 columns we have. And here we would be considering second and third. So 0, 1, 2, 3. And this would be 4. Right guys, but as we know here, whenever you work on this, how many columns do we have 5, but how can here we have, how can we have 6 here? It means that it all starts with user ID. So 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, which means that age and uh, let us just yeah, age and estimated salary. So age and estimated salary would be a part of my independent variables, while purchased or not would be my dependent, which means that I'm trying to understand that based on age and salary of a person, would an item or would something be bought or not. This could be very crucial in making decisions when you might want to open a store, or when you might want to check about how that area works, or cases like these. So yeah, based on age and estimated salary, I would be trying to understand if the item is purchased or not. So then comes the next step, which is splitting the data. And splitting the data, I'm using 30, which is my test size, and 25, which is my train. All right, so here we have test set and train set, and then after this we would be now working on the feature scaling. So when we talk about feature scaling, it is the same step which we did earlier too. It is the same standard scalar, the same library, that is sklearn dot preprocessing. After which I would be passing the standard scalar into another variable with the name sc. After which this x train values would have sc, and this would go and fit and transform to train model, while x test, which we were talking about, x test would be, more on the lines of transforming and sticking to the x test data set, or sticking to the other part of x test, right guys? Then now that we have understood how and what, and like the basic differences between pre-processing, standard scalar, let us now go further. So let me just again try to summarize from the beginning. It's all the same: libraries, data set, data split, feature scaling, and here we would be applying to model, right guys? So here when we talk about in this part sklearn preprocessing standard scalar, so x train would go and fit and transform to the model, while x test would transform itself. After which I would be using my predict. So here we are now working on predict, and as we all know, predict would be a functionality which is used in machine learning to see how this model is actually performing, right? So I'm passing the predicted values of x test into y pred, and then we are now coming up with the confusion matrix. And this confusion matrix, as you can see, it's a definition of confusion matrix, wherein the math C, and I mean it's a whole lot of understanding about what confusion matrix does. Okay, now that we all know what confusion matrix is, I don't think we have to delve deep into it. Okay, so I'm importing my confusion matrix, and then I'm using the other two models, which is y test and y pred. And guys, so when I do that, or like when I use my confusion matrix, right? So here we have CM, right? So this is the confusion matrix that we have obtained. And what does the confusion matrix say? It says 72 plus 37, that is 9, 109 by 11, which is still a better deal. But then, right? But then as we go ahead and we try to come up with a plot for the training set and the testing set respectively, we would be able to actually visualize and understand the difference between RBF and a linear regression, or probably RBF and a linear classification using SVM. And here the only difference that would come up is kernel would change to RBF. Right guys, so let us now enter and wait for the result to come up. Let us now go to the plots, and here it goes. So here, if this would have been a linear variant of separation, then we would have had a plot something like this, or probably something like this. But these kind of lines or these kind of hyperplanes or this kind of separation would be of no use in this particular case. And it is to overcome these kind of challenges, or it is to overcome these kind of complexities while we are trying to code, is the reason behind coming up of RBF or probably Gaussian or different type of kernel methods. And guys, then going forward, here again, let us now execute the second part of the code. This is the other part of the code. And if we can note, okay, let me just scroll this. Right, we can notice that this graph and this graph are different because this is from the training and this is from the testing. Testing has only 30% of data while training has 70% of the data, which is also one of the predominant reasons why this training set is looking heavily populated, while the testing set is looking a bit on the lower side. It is only because of the quantity and has nothing to do with the logic. Right, guys? So this is an understanding about how we work on SVM and what it is. But notwithstanding this, let me just clear the screen, go back to the slide. Right, here it is. Notwithstanding this, we know that SVM can be performed using R or Python. And here, I'm just trying to list out certain key features which might become very important. Okay, here we try to carry out the plotting in the nth dimensional space. It is not always 1D or 2D. Right, guys? And also here you have some frontier methods for separating two classes, and these methods are called as kernels. Now, how does this work? Basically, it comes up with a line, and this line is called as a hyperplane. And why is it not called a line is because of the fact that this plane, it cuts the whole region. So this plane has information here also, and this is a 3D view when we are trying to cut a mountain. Okay, so I hope even this part is now understood. So yeah, this is about SVM, and this is where, how, and why we use this, kernel methods or kernel techniques, or probably we use these kind of algorithms to come up with solutions for different kinds of data set. Now, as we have seen, when we're using a linear, this is how your data set would be split like. And here we would be trying to find out the relationship. But this is how it is when it is for non-linear. Here it would try to come up with the best boundary. And these best boundaries are based on 1D or 2D or 3D, or what is it that you select, which variant of polynomial would we want to select. That is the most important question here. Right, guys? So I hope you have understood where, why, and what, and how we use SVM. And if in case you feel that's a yes, then please do not forget to hit the like button, and also do not forget to hit the bell button followed by the subscribe, because when you do it, you would be having access to a plethora of videos to watch from, and also a great number of technologies to choose from. Thank you very much. This is me, Varun, your trainer, your mentor, signing off. Wishing you all the best for all your future endeavors. Have a great day and thank you.